I just want to preface the video by saying I did not intend for it to be this long, but kind of as I was researching and as I was writing up some of the code for this, the scope of the project just kept expanding and expanding, so here we are. I definitely still hope that the video is a useful resource for you guys, and to that end, I'm going to be linking kind of the code that I'll be showing off in the description, so you as to aid you guys if you want to write your own compilers and use this as a reference. I think that would be pretty sick. But anyway, I guess I should start off by actually showing you what the program does. So here's a program in the language we're interpreting. It's a form of pseudocode because I thought that's something that everyone would be able to understand fairly easily. And as you can see, when I run it, just input the number that I need to, and it just adds up all of the numbers from 0 to whatever number I input. It's a really simple program, and it's a really simple language as well, but I'm hoping that some of the tools and techniques that I show off in this video can kind of help you guys to write even bigger projects or whatever else you work on.
So the first stage of parsing any program is the Lexing stage. And just before we kind of get into some examples, I kind of want to motivate why do we even do this? And the reason is, it essentially boils down to the fact that parsing is already a fairly complicated task for a human to figure out, and we essentially try to group characters into sort of more higher level tokens that we can understand, so that we can just reduce some of the complexity for ourselves when we actually have to write the parser. So for example, it's a lot easier to deal with one object called an int literal, right? Rather than having to constantly worry about the fact that your int literal is these characters and there's a bunch of special cases. Essentially just makes the code easier, right? And pretty much if you look at any modern programming language, they all have this step, because it's just kind of good practice, and we've sort of found out from just years of parsing experience that this is the way to do it. Anyway, so I'm gonna get straight into some of these examples. Let's see how the computer can understand this expression here, 127. So as I hinted at before, the way a Lexer kind of works is it's sort of a state machine, in the sense that it just remembers the character it's seen kind of previously and uses that to decide what to do with this next character. So we'll start off with the state machine, with the Lexer being empty, so it hasn't seen anything, and it sees a number 1. And the number 1 kind of tells it that, okay, which of these options could we be dealing with? Well, it's either an int or a float, right? Because nothing else really makes sense to start with a number 1. And incidentally, that's actually why most programming languages don't allow you to start variable names or identifiers with numbers, because it just makes it parsing so much easier when you can just rule it out directly. Anyway, so it starts with 1, so we know it's an int or float literal, right? And we also know what sort of characters are valid numbers. So we'll just keep trying to get characters until one of them is invalid. That way we know that we have a number, right? Or we have the largest number possible there, which is probably what the programmer was trying to communicate. So we take 1, and then we look at the next token, 2. That's also a valid number, so that becomes part of our number. And then we look 7, that's also a valid token, so we take that in. And then we get a space or end of file. And that kind of tells our Lexer that, okay, that's not a valid token. A space is not a valid part of a number, right? So we terminate the number here, and this is what gets passed into our int literal, right? We have an int literal with value 127, right? Similarly, we do a very similar process for parsing variable names. So incidentally, output is kind of special here because it's actually a keyword in pseudocode. So we start off by parsing by looking at the O, and then we realize that we're in some sort of either an identifier or a keyword, right? So we just see that we have O, we get the next one U, T, P, U, T, and then we get the space. So just like what happened in this int literal case, we we realize that, okay, anything after this space is kind of no longer part of the literal. So basically, we know that this is kind of one thing, or output is like one token, right? The only thing is now we need to figure out whether it's a identifier or a keyword. And this can simply be done by just comparing it to a list of keywords, right? Most languages only have like 20 to 30 keywords. So we just check, and sure enough, output is a keyword. So we just create a Lexer token with the value of keyword output. And then we just resume. We just start processing color. So we know that because this is a space, we have to like start a new token. We see the C, which again lets us know that we're probably dealing with the identifier or a keyword. COLOR. Grab all of that. There's a space there, which tells us that again, this is one unit, or this is one token. And then from that, we basically again compare with the keywords. We realize that color is actually not one of the keywords in our language. So we decide that color has to be a variable name, right? And just a final example, and this is going to involve like a bit of punctuation as well. So again, we start off really similarly, and I hope you're seeing like, I hope you're starting to get a feel for how Lexing isn't actually that complicated. It's just doing the same thing just multiple times. So we start off with an S. Again, we realize we're an identifier or a keyword. We grab U, we grab M, then we encounter an equal sign. And again, we realize that identifiers can't have equal signs in them, so sum has to be kind of one unit. Okay, we check, is it a keyword? No, it's not, so it has to be a variable name or an identifier. So we get that token. Next, we encounter this equal sign. So we realize we're probably dealing with some form of punctuation here. But the tricky thing is, punctuation can also have different lengths. So we need to do a little bit more work. So similarly, we realize, okay, we have one equals, but it is possible that the next character can be an equals, and this is actually not an assign expression, but this is actually checking whether sum is equal to 0, right? So if sum is equal to something, I should say. So we check the next token and we realize, oh wait, no, this is not another punctuation. Therefore, we can actually split it like this, because now we know this equals has to be independent, right? Even though, again, these spaces did not actually exist in the source code, we can, like the Lexer at least, can make a distinction because it realizes that this can't possibly be a type of punctuation. And after that, when we realize that this is also a separate token, we check it. It's a 0, which means it's an int or float literal. We go to the next character, but it's empty, or it's like end of file or something. So we terminate the int literal, and from that whole process we realize that this is an int literal. So yeah, that's really all there is to it. It's just basically taking characters and converting it to tokens. And now let's go take a look at how we'd actually implement this.
Here's basically the code for the Lexing Stage. And like, I think the main thing I wanted to highlight here is the function lex, because in essence, that's all there is. It's Lexing is actually a fairly simple process. Like in the code, it can be some of the ideas can be a little bit tricky to wrap your head around at first, but I think I'm hoping that just looking through this function, it should become like a lot clearer. So literally, we're doing exactly what we did by hand on paper, which is we're finding token. We're getting like a character, right? In like a loop. We're just constantly getting characters from our character stream, and then we're checking if the character is a digit. Then it's going to be an int or float literal, right? So we just constantly after that just keep taking in characters and then return an int or a float literal based on whether it has a decimal point or not. Simple enough, right? We do a very similar thing here with strings, right? We check if it's alphabetic, and afterwards we keep on taking characters that are alphabetic and we put them in, again, just a buffer, and then we create a new literal, like an identifier or a keyword based on that buffer. Punctuation is handled in, again, a really similar way. We just match the tokens. If it's some type of punctuation, then we just take that punctuation, return the correct token for it. And essentially that's all there is to this function. Just some other things to note is basically we're just doing some error handling stuff here with the parse error. It's nothing too complicated. We're just using that just to make the control flow simpler. But other than that, Lexing is a fairly easy process, and I hope that's kind of more apparent now that we've kind of gone through some of the intuition and then also the actual implementation of it.
So the next obvious step in writing this interpreter or compiler is the parsing stage. So after Lexing, we've turned our token stream into a bunch of these Lexer tokens, right? And now from that, basically, we want to kind of bundle them up into blocks that map to our programming language constructs, such as statements, or maybe if you're dealing with a language like C or C++, that could be functions and declarations and structs. Right? So just before we dive right in, I wanna just reassure everyone, it can seem really daunting at first, especially because if you look at the statement, the data structure for statement, right? It contains a bunch of individual different structures for each sort of individual case, and each of these contain their own complexity, right? And it can seem really daunting at first, but here I just want to, if I can steal a quote, highlight the unreasonable effectiveness of using small functions with singular tasks to break down a complicated problem, because I hope from this video you'll see how even a problem that can seem as complicated as compiling something can actually be broken down really effectively by just writing small functions that do one thing really well. Okay, so let's jump straight into it with some tokens. The parser just needs to make sense of these and produce well-formed statements out of these tokens, right? And in actuality, when you really consider how languages are designed, you'll notice that it's actually fairly simple to do that. So we'll start off by seeing this input statement, right? And that immediately lets the compiler know that our input token, and this immediately lets the compiler know that our first statement is an input statement. So we know it's an input because of the keyword, right? And if you just think about many of the languages you use, they'll also have similar constructs like that in order to make parsing easier, right? Now, after an input statement, the compiler expects some sort of identifier. So, so this function will be a parse statement function. And I think this will kind of make more sense as I carry on this kind of, control flow tree. After it sees the input token, it's going to try to parse an identifier, right? So we'll have a we'll have a parse identifier. And because this is successful, it finds n. We can now take these two tokens and group them together as a finished block, because this is essentially now a statement that we can actually execute, which is super cool, right? And now it just continues, because now that one statement's over, we just call parse statement again, and we try to parse another one. All right, so after that, we're just going to try and parse another statement, and the compiler sees the sum Lexer token, and it realizes that, well, this is an identifier, right? And again, if we look at the statements we have here, there's only one statement type that can begin with an identifier, which is an assign statement. So it realizes when it sees this sum token that we're dealing with an assign statement. And the compiler knows now that it's going to expect an equals. So it's going to be a try parse equals or something. Right? that works. After that, it's going to try to parse an expression. So this is where things get kind of complicated, because expression parsing has a lot of like inbuilt complexity in terms of like operator precedence and stuff. But because this is a simple example, we won't really get into it. Essentially, what parse expression does is it tries a bunch of things, because expressions, if I just bring this over here, expressions can have a bunch of different forms, right? And it's not immediately obvious like which form we're dealing with. Right? So it's gonna basically just try parsing all of these. Try parse. And so on and so forth. Right? And it's basically just going to check what sort of object do we have, what sort of like object are we assigning to the variable sum, right? And in this case, obviously, it's an integer, it's 0, right? So basically, it's gonna create an expression of type int literal, and that's gonna basically exist here. Now, there's kind of a caveat here, because we could have some arithmetic operation here. Like this could be a 0 plus like 5 or something, right? So it does also have to check that. And that's where we use this function called try parse binop. Which basically checks the next token and sees, oh, is this like a plus sign or a minus sign or something? Basically, is this an operator that like would imply that this expression is not just a singular 0, but it's actually a binary operation. In our case, this fails, right? This returns like false or something, which lets us know that this is probably the extent to our statement. So that's good, because now we have a second statement that's been parsed. And essentially, this is all there is to parsing. It's just a very sort of logical and methodical process where we essentially use the information we have, and then we just try all possible continuations. So I'll give just one more kind of example to highlight this point. In pseudocode, there are three different types of loops. Three different types of loops: for loops, while loops, and until loops. Right? And when we see a loop keyword, again, we parse statement, we see loop. We don't know which type of loop this is, and each type of loop has like different requirements for being parsed. So we just try all three of them, right? We try while, try for, and try until. And in this case, it's actually a for loop. Right? The actual syntax for that is loop I from some expression to some other expression. And essentially, we'll expect the try while and the try until to fail, because the syntax for those loops is loop while, loop until. But if you have a for loop, it's going to be loop and then an identifier. And again, this is basically the steps that go into parsing. It's just basically trying every single combination. And suppose this was maybe neither of them. Maybe this was like the word from, right? Maybe I made a syntax error. That's when all of these would fail, which would result in this parse statement function failing, and that would result in a compiler error or an interpreter error. And that's kind of how error handling gets built into this, because when you actually break down the process of parsing and error handling, it can seem really difficult when you're trying to imagine the whole system. But if you just work with these small detailed cases and you have like a bunch of them,
you can create like a really complicated system. And I think one really good way to see that is to jump straight to the code. So let's do that. Here's the code for most of the parsing, and again, it does kind of. I'm hoping you'll see like how similar this is to what we did on paper, right? We're just constantly just taking in tokens and trying to parse a statement with it, while like there are some tokens left, right? This parse statement function, it's basically we're just matching the first token, right? If it's an identifier, then we know it's quite likely that this that the statement we're parsing is an assigned statement, right? So we do just again what we did on paper. We check if the next tokens are equal, and then we check if the next token's an identifier, right? For example, here's the input statement. We just if we see the keyword input token, then we just try and look for an identifier and we return that statement. And to be completely honest, that's basically all there is to parsing as well. We're just looking case by case and trying to match things. Things get a little bit more complicated when we go to some of the loops and like if statements, right? Essentially here in the loop, what we need to do is when we detect the keyword loop, then we're just matching what type of loop it is, whether it's a while loop or until loop, or a for loop. And if it's a for loop, then we basically need to get the condition out. Actually, for any of the loops, we parse the condition, and then we parse a new set of statements, which will be here, new set of statements here. And basically, these statements are in the body of the loop. So we just kind of use recursion for that, right? We already have a parse statement function, and we can just use that guy directly in here. And I think that just makes this whole process like fairly easy. The only other thing I want to talk a little bit more about is this parsing atoms and parsing binary operators, because this is, I think, one of the points where I got stuck on when I was trying to write this, because it is fairly confusing. So to do that, let's move back on to paper so I can draw some stuff out. So before we jump straight into like evaluating, I want to take a quick detour into binary operation parsing, because it's one of the types of parsing, one of the techniques in parsing, I should say, that I had a lot of trouble with. And I think some of the tools here can be applied in like a bunch of different contexts within parsing, like to parse more complicated sort of data structures. And I think it's worth kind of highlighting that for a moment. So I've just printed out the actual code, how my pseudocode interpreter handles binary expressions and atoms. So quickly, just going over some data structures, right? These are the Lexer tokens we'll be getting in. All this parse atom function does is takes these tokens and converts them into expressions. And the parse atom function only handles the basic expressions, so it does the literals and identifiers. Binary operations are handled with, as you might expect, parse binup, and a binary operation looks like this, right? And the kind of job of this function is to take kind of these tokens produced by parse atom and join them together with binary operations. So just quickly, I want to show some of the usage, show how these functions are used, like a lot of times in the code. So in my interpreter, this is like a pattern you'll see really often, which is we parse one atom and we call it like left or something, and then we try to parse a binary op based on that. And this is kind of just a general technique that I'm using in like my pseudocode interpreter to handle like complicated binary expressions. So what is the actual challenge with parsing binary operations? It primarily boils down to order of operations, because you can have a function you can have like an expression like this. 3 + 4 × 5, and that needs to be parsed in this specific way. because of order of operations, right? And this is in contrast to, I guess I'll just use the same numbers, just to make the point, but something like this, which is going to be parsed kind of in the exact opposite way. Like this, right? And this is actually a surprisingly hard task to do. It's surprisingly hard to conceptualize how to solve this problem, because there's actually a lot of kind of intricacy here that might not be immediately apparent. Because so far what we've been doing is we've been just taking one token and then taking the next token and assuming that the previous token has information as to how to parse this next token. And that's kind of not really true with this case, because here, right, when we get to this multiply sign, when we're parsing, we parse the 3, right? We can determine it's an interliteral, and then when we parse the multiply sign, we actually don't know which configuration it's going to be. Because if this was something like an exponential, we know that the exponential, it would be something like this, where the multiply sign's on top and the power symbol or the exponentiate symbol is kind of down here. But if this one's an addition symbol, we know addition has like a lower precedence, or rather a higher precedence than multiplication, right? That's why it's at the top of the tree, because it needs to be evaluated last. So kind of we get a lot of complexity arising from the fact that it's hard to kind of parse this in a very like linear way. But there are some pretty nifty techniques that you can use to kind of alleviate the problem. We're going to go through it with this function. So kind of in parsing an expression like this, what we do is we first parse the first atom, right? So that's very simple, right? We get the 3, we determine it's an expression. After that, what we do is we call parse binary operation on this, and we pass this token into it. And basically what that does is this function just checks, okay, is the next token some sort of operation, right? If it's a punctuation, that's not a sign. If it isn't, it just returns 3, right? Because that is also a valid expression. Just a single atom is also a valid expression. However, if, for instance, the atom contains like, if the next token's a plus sign, we can kind of assume that it's being added to something else. So then what we do is, I'm just going to ignore all this precedent stuff for now. We try to parse the next atom, and then we basically return this structure here, our binary op structure, right? Where our left is this left expression, right is this right expression here, and our punctuation there, right? And it works perfectly for cases like this, because we just go 3 plus 4, right? And then we obviously recursively call parse binary operation here on our right expression, and then it realizes that, oh, 4 is also a binary expression with 5, so this tree kind of goes down here, and everything's fine and dandy. The only problem is it breaks down in this case, because in this case we want our first operation to actually be lower, just because it needs to be evaluated first, because multiply, order of operations, BEDMAS, all of that stuff, right? And that's kind of where the precedence comes in, which is really, really cool. So essentially what we do is we assign each operator like a precedence value based on like how high or low in the tree it has to go. For example, addition has a lower precedence than multiplication, because multiplication goes first. Has to be evaluated first, I should say. And the way we actually implement that in the code is if we say that the parse binary operation takes like a starting precedence value. So at the start of an expression, it's 0, right? Which you can see from this 0 here. But then it takes the value of the new operator that it's just evaluated. So in this case, it takes the precedence of plus sign. And only if the precedence of the next operator is higher, i.e. it can go lower down the tree, does it parse it normally, right? So if new precedence is greater than precedence, so for example, when we've already parsed up to here, we see multiply has a precedence of I think 2, which is higher than plus. So it just works. Now, if the precedence of this. So for example, in this case, right, we've already gone through multiply. So when we get to this point, our precedence is already 2, and plus has a precedence of 1. So this if condition doesn't actually work. So instead, what happens is it just directly returns our left node, right? It just directly returns the 4, and it basically creates this structure here. And then this line over here. So I'm just going to track the calls for this just to make it a bit more clear, right? We first call parse bin op. And like heuristically, we're passing in the 3, and that's kind of about it, right? This is abusive notation, but it's fine, right? And this guy he finds the next operations of multiply, so he keeps that in mind. And then he finds that the next item is a 4, right? And then he calls parse bin op on this 4, right? So and what that does is, again, does the same thing, finds this plus sign here, and then it realizes that the precedence of plus is actually lower than the precedence of multiply. So it can't actually parse this 5, because the 5 should actually go above, right? It should be this sort of structure instead of this one. So then it just returns directly. It directly returns just the 4, which means this function currently is working with the value 3 times 4. This little tree is what this function has. And then this function runs this line, where this whole expression becomes the left node, right? So it calls parse bin op, of this tree, essentially, and because the tree kind of has a precedence of 0, or rather it has the previous precedence, right, before the multiply, which was 0 because this is the start of the expression, it's able to just directly join with this plus sign, and it creates this tree, right? Now, this was super confusing for me at first, right? And I would definitely suggest, again, just take some paper, some pens, and just work through a few examples with the code, because you really need to do it yourself to visualize it. But I think I just wanted to highlight this technique because it's a really powerful way to encode precedence and ideas like order of operations into parsing, which, I mean, it might seem like really specific for, oh, you can only use this for equation parsing, but these ideas are like really general and like really applicable to like lots of different kind of techniques within like parsing and just general programming. So I just wanted to kind of take a quick detour to highlight this. Now I'm gonna go and kind of walk through how we actually evaluate these trees that we've parsed. Alright, now all that's left is for me to make good on my promise that I made at the start of the video and actually show you the fully working interpreter and explain the last part of it, which is actually running all of the code. So this is the same example program from the start, right? And as you can see, it just runs completely as you'd expect it. You just pass in the file name and it just kind of works. Now, I want to just refer back to the main function here of our program just to show how simple, how simply you can conceptualize the actual interpretation stage, right? All we really do is we create like this hash map of variable names and this struct called PSC objects, which are basically is the kind of data type that the interpreter uses internally to represent variables, right? And it can just take 4 different types: ints, floats, strings, and booleans. It's quite simple. And that's essentially all there is to it. After that, all we need to do is provide this function eval to evaluate each statement, and that function it basically writes itself, because after we've done all the hard work of parsing, running the actual code is fairly simple, right? Like for example, I'll just pick a random statement, the if statement. It just takes the if statement, opens the branches, checks the conditions. The reason why there's branches, by the way, is because the if statement includes if else as well. So, but that's just a technicality, right? It just opens the conditions, and then it just checks the condition, and then if the condition is true, it just evaluates all of the statements in that condition. And of course, they can be an arbitrary number of statements. You can have nested ifs, and it just kind of works. Just like that. The while statement again functions really similarly, right? Just evaluates, checks the condition repeatedly, and then just evaluates all of the statements in the body of the while, right? And then, for example, the assign statement, it literally just does exactly what you'd expect. It just evaluates the expression that the assign statement is paired with, and then just puts that expression into the hash map with the variable name that it's assigning to. Right? And that's basically all there is to actually running the program. We've already done the hard work of lexing and parsing, and basically the rest of this file is just a bunch of boilerplate, like here, to just make arithmetic operations work, because like you have to compare ints and then floats and all of that stuff. But yeah, honestly, yeah, and to be honest, that's all there is to it. I hope now you guys kind of have more of an intuition as to how to actually write your own languages, write your own interpreters or whatnot. And no promises here, but I am currently working on some more stuff on my own on actually writing like a fully fledged compiler, because as you can see, like a lot of the ideas here are definitely applicable to a compiler. It's just that instead of having a simple front end where we just evaluate each statement, a compiler would have to write assembly and output that. So no promises on that, but might be something to look forward to on the horizon. But anyway, other than that, thank you so much for watching, and I hope you learned something interesting.